Hello everyone, and welcome back to the Fluctus Channel. The machine-assisted rugged soldier project, MARS, is built around one dangerous battlefield problem. Soldiers often have to approach mines, obstacles, and enemy positions before anyone fully understands the terrain. Engineers clearing a route may face hidden explosives, direct fire, rough ground, and narrow paths where a crewed vehicle can become trapped. The project explores how autonomous and semi-autonomous machines can move that risk away from people while still carrying the tools needed for combat breaching. At Fort Cavazos, Texas, the 36th Engineer Brigade used the project to demonstrate robotic support during a breach. One of the central systems was DARPA's RACER, short for Robotic Autonomy in Complex Environments with Resiliency. RACER is not simply a remotely driven truck. Its purpose is to let an unmanned vehicle perceive terrain, select a route, avoid obstacles, and travel at useful speed without a person steering every movement. The program began with controlled experiments before moving toward operational use. During RACER Experiment 1 at Fort Irwin, California, a safety operator monitored a fleet vehicle as it crossed a prepared course autonomously. Sensors mounted around the vehicle fed information into the autonomy software. Cameras and ranging systems identified rocks, slopes, bushes, ditches, and routes ahead. The computer then compared possible paths, chose one, and continuously corrected steering and speed. The desert made an ideal proving ground because it punished weak navigation. Loose soil reduced traction, dust interfered with visibility, and sharp changes in elevation forced the vehicle to judge whether an obstacle could be crossed or should be avoided. During later testing in the Mojave Desert, RACER vehicles moved through increasingly difficult terrain without following a smooth road. They climbed, descended, crossed uneven ground, and threaded between natural obstacles while engineers watched from control stations. Monitoring is essential because autonomous testing creates a second mission behind the vehicle. Teams track position, speed, system health, sensor performance, and every decision made by the software. Early tests often used a safety chase vehicle or operator ready to intervene. As the program matured, soldiers employed RACER in force-on-force experiments without a dedicated babysitter following close behind. That change marked a major step from laboratory autonomy toward a system that could function inside a real formation. The machine-assisted rugged soldier demonstration then connected autonomy to combat engineering. RACER was paired with equipment used to breach minefields, including the M58 Mine Clearing Line Charge, or MCLC. The charge is normally launched across a suspected minefield, creating a path through mines and obstacles. Carrying that system forward exposes crews to the exact danger they are trying to remove. An unmanned vehicle can transport the heavy charge, approach the breach lane, and place the system where commanders need it while soldiers remain farther back. This does not mean the robot replaces engineers. Soldiers still plan the breach, identify the lane, coordinate fire support, confirm safety, and decide when the charge should be used. Racer becomes a moving tool inside that plan. Its value comes from reaching dangerous ground without demanding that a driver sit inside the vehicle. By 2025, the project was demonstrating that autonomous vehicles could support real combat tasks rather than simply complete obstacle courses. The experiments also prepared Racer for transition beyond DARPA. The rough terrain vehicle, the soldiers directing it, and the mine-clearing system all pointed toward a future where tracked or wheeled robots scout routes, carry explosive tools, recover damaged equipment, and absorb the first risk of a breach before human crews move through. In future, autonomy becomes protection, measured not in armor, but in distance from danger. Autonomy is also changing military aviation, where the risk is measured in altitude, distance, and exposure to enemy air defenses. The U.S. Air Force's Skyborg Vanguard program was created to explore affordable autonomous aircraft that could work alongside crewed fighters. Instead of placing a pilot in every jet, Skyborg focused on a digital autonomy core able to control aircraft, process information, and support human decision-making during complex missions. The goal was not to build one perfect drone. It was to test software that could move between different aircraft and allow commanders to use lower-cost, attritable systems where losing a vehicle would be serious, but not as catastrophic as losing a crewed fighter. This concept led into broader autonomous aircraft experimentation involving vehicles such as the UTAP-22 and the XQ-58A Valkyrie. The XQ-58A first flew in March 2019 at Yuma Proving Ground, Arizona. Its shape reflects the mission: swept wings, a compact fuselage, an upper-mounted air intake, and no cockpit. The aircraft was designed for long-range, high subsonic speed, and the ability to carry sensors or weapons while operating with a small logistical footprint. It can launch without a conventional runway using a ground-based system, then recover by parachute and landing equipment. During autonomous aircraft experiments, engineers tested how unmanned jets could receive mission commands, maintain formation, respond to changing conditions, and work with other aircraft. A human still defines the objective and rules, but the aircraft can manage many lower-level tasks itself. That reduces the need for constant stick and throttle control and allows one operator or aircrew to supervise several robotic teammates. The Air Force also used the Advanced Battle Management System Gateway 1 experiment to connect an attritable aircraft with F-35s and other platforms. The point was not simply flying together. It was sharing information across different networks, so one aircraft could detect a threat, another could process the picture, and an unmanned teammate could move forward without forcing the crewed fighter to take the first risk. The Marine Corps later pushed the XQ-58A into its PAC-P effort, short for Penetrating Affordable Autonomous Collaborative Killer Portfolio. The program studies how an autonomous aircraft can support expeditionary forces, extend sensing, and deliver useful effects while working with marine aviation and joint systems. During joint test missions, crews launched the Valkyrie, monitored its route, evaluated communications, and collected data on how the aircraft behaved as part of a team. These experiments represent a new idea of combat mass. A force may not need every aircraft to be a highly expensive, crewed platform. Some unmanned jets could scout, relay data, carry electronic systems, or draw attention away from manned aircraft. Others could serve as weapons carriers under human control. The advantage comes from numbers, range, and the ability to accept more risk. The military has also created autonomous aircraft by transforming older fighters. The QF-16 converts an F-16 into a full-scale aerial target that can fly without a pilot on board. Ground crews can remotely control it while test organizations use the aircraft to evaluate missiles, sensors, and air defense systems against a realistic, high-performance target. The QF-16 preserves the speed, maneuverability, and radar signature of a real fighter, making training more demanding than using a small drone. Before it, the QF-4 performed a similar role using retired F-4 Phantom II aircraft. Its final unmanned flight marked the end of one era and the transition to the QF-16. These conversions reveal how autonomy can give old aircraft a second mission. Instead of going to storage, a retired fighter can become a robotic target, helping crews test the weapons and systems that will defend future aircraft. The same autonomous shift is moving onto the ocean. Unmanned surface vessels, or USVs, are boats designed to operate with reduced crews or no crew on board. Some are remotely controlled, while others can follow routes, avoid hazards, and perform missions with growing levels of autonomy. Their value comes from persistence. They can patrol, collect data, and enter dangerous waters without placing sailors directly in harm's way. Small USVs are especially useful in shallow coastal areas where larger ships cannot maneuver easily. The Manta's T-38 Devil Ray is one example. Its low-profile, high-speed, and sensor payloads allow it to survey waterways, patrol coastlines, and support intelligence collection. During demonstrations, operators prepared the vessel, checked propulsion, communications, cameras, and navigation systems, then launched it into the water. Once underway, the craft could relay imagery and position data back to a control station ashore or aboard another ship. Shallow waters are crowded with sandbars, debris, fishing boats, piers, and narrow channels. Operators monitor the route and redirect the craft when traffic, weather, or mission needs change. Larger unmanned vessels extend the concept into open water. The USV Ranger arrived at fleet activities Yokosuka, Japan, as part of the Navy's effort to test unmanned systems with forward forces. bringing an unmanned ship into a busy naval base requires discipline as receiving a crewed vessel, harbor coordination, tug or escort support when required, pier planning, line handling, communications, and maintenance inspections after arrival. Ranger had already demonstrated long-distance operations and participation in fleet experimentation. During RIMPAC 2022, unmanned surface vessels operated alongside crewed warships in one of the world's largest maritime exercises. The purpose was to learn how autonomous vessels could share information, follow tasking, and remain useful inside a fleet that includes destroyers, aircraft, submarines, and command ships. International Maritime Exercise 2022 expanded the picture even further. Task Force 10 brought together unmanned aircraft, surface vessels, underwater systems, and partner nations across the Middle East. Rather than treating each drone as an isolated machine, the exercise connected them into a network. A surface vessel could watch a sea lane, an aerial drone could investigate a contact, and a command center could combine both feeds into one picture. This matters because no navy can place a crewed ship everywhere. Commercial traffic, fishing fleets, narrow straits, and long coastlines create more space than traditional patrol forces can continuously cover. Unmanned vessels can increase the number of sensors at sea, keep watch for longer periods, and send crewed ships only when human judgment or force is required. From Racer crossing desert terrain to Valkyrie flying beside fighters and Ranger entering the Pacific Fleet, autonomy is spreading through every domain. The machines differ, but the purpose remains consistent. Extend reach, increase awareness, and move the first layer of risk away from human crews. That's the end of this video. I hope you enjoyed it. Make sure to subscribe to this channel so you don't miss any of our new content. See you next time.